is by Greta Panova, who will talk about Kronecker coefficients in the tensor square, conjecture, and unimodality.
No!
Typo change.
And complexity.
So the reason for the change in title and topics is that last week I was at the Stanley 70th birthday conference where most of you were also there, even more of them, and I was talking about the unimodality aspect of all this, of these things, and because it fits better with, well, with STEM. So now I'm going to talk about these other two topics instead, the taxaxial conjecture that Ernesto already mentioned, and complexity in the sense of computational complexity, P versus NP, that sort of thing. So, okay, so hopefully you were all here previous talk, so I don't need to redefine everything, but what is this about? We have irreducible representations of the symmetric group, not to be confused with the general linear group. And so they're indexed by partitions of n. Then the question is, if we take two irreducible representations, take their tensor product, which is also a representation of the symmetric group, how does this decompose into irreducibles, or in other words, what are their multiplicities? And these are exactly, their multiplicities are exactly the Kronecker coefficients, G, lambda, mu, and mu. And there is, so I will just mention this view through symmetric functions, that there is this tensor product becomes this Kronecker product star on the ring of symmetric functions, where these are exactly the structure constants for the multiplication of show functions. And this is what most of these proofs, what is underlying them is this kind of approach to symmetry. And then of course there are the characters, which there is also the same notions as in the representations. One can transfer to the characters and then take inner products. Then these multiplicities are exactly the inner product of the tensor product of two characters and another one. They are computed by the Murnaghan-Nakayama rule, and as you see, they're alternating sum of over Murnaghan-Nakayama tableau. And from representation theory of finite groups, we can see that this guy here evaluates to this. Well, this formula is kind of a little bit useless because these guys can be positive, negative, and potentially very, very large. So we have this huge sum of big things of different sizes. So you can't, but on the other hand, this is always a non-negative integer. So that doesn't help much. The only thing that it helps is that these guys are invariant under permuting the partitions, as can be seen from this form. So that's why we'll write them in line notation as opposed to the little Richardson coefficients, which one partition goes on top. And so what's the motivation of the whole problem? Well, it's, first Murnaghan asked the question motivated by the fact that the Littlewood-Richardson coefficients, which are for the analogous problem, but for irreducible representations of the general linear group, well, they have a nice combinatorial description, everybody here knows. And now the question was, well, what about replacing these representations with the representation of symmetric group? Why can't we have a nice combinatorial description for the same guys? And further motivation is that actually the Littlewood-Richardson coefficients are special cases of the Kronecker coefficient. So if you take your partitions such that everything but the parts below the first row add up, like in this way, then you actually recover a single little Richardson coefficient for any partitions like that, lambda, mu, and nu. So this is a generalization of those. And so what happens is then, well, not that much. So this question, I didn't give the year here, but Mornagan basically did this in 1938, 75 years, well, 76 now, years ago, and I mean, there are some progress when, for very special partitions, the best thing to this moment is John Blazek's combinatorial interpretation when one of the partitions is a hook and the other two are arbitrary. So, alright, so now let's look at the problem from different angles. So let's not try to find a combinatorial interpretation, but see what else we can do or say about this Kronecker coefficient. And here is one thing that Ernest already talked about. This is the Saxel conjecture. And it was motivated by a similar result for finite simple groups of Lie type, where there is a particular irreducible character whose tensor square contains every irreducible representation. It's the Steinberg character. So Saxel then conjectured why is this not true for the symmetric group, and so and he asked why do we take particularly this partition? Well, we need two things. We need it to be self-conjugate so that it contains the sign representation. We also need it to have large enough dimensions so that, at least dimension-wise, this thing is bigger than what we want in the rest of the sum. And from then on, it is just a nice partition. And of course, so if we take the square here, it's not going to satisfy this because there is one particular, so n-1 partition that it doesn't contain. But other than that, we could choose different partitions. And I will show results that call for different partitions as well. So here is our result. Basically, we are saying that if we take tensor square of these guys, for any large enough k, they are going to contain all partitions which look like that. So there are two rows and a finite number of boxes on the bottom, or hooks of any length and finite number of boxes in this part here. And so, as I mentioned, the things hold not only for this partition, but if we take a square without its bottom right corner, which is also self-conjugate and has large enough dimension. And what is the main ingredient in this proofs is the following sort of character lemma. And it turns out that if we have self-conjugate partition mu, and any partition lambda, then if the character of lambda, the reducible character, evaluated it, what these are the principal hooks of mu. If this character is non-zero, then actually the Kronecker coefficient mu, so tensor square, and lambda is strictly greater than 0. So lambda, the reducible representation corresponding to lambda, is contained in this tensor square. And it's based on the reduction to the alternating group. So here is one very simple example. Suppose that lambda and mu are the same partition. Here are the principal hooks of mu. And the character is plus or minus 1, because by the Mornagan-Nakayama rule there is only one way we can fit such long ribbons in the same tableau. So if it's non-zero, then we recover a result, earlier result of Besson-Roth and Benz, that for every self-conjugate partition, tensor squared contains that particular, the corresponding representation. And so later we actually strengthen the result by saying that this Kronecker coefficient is actually greater than or equal than the absolute value of the character. So, and that's actually, that has other implication towards this unimodality that I'm not going to talk about. So how does this lemma apply in our case? Well, now we need to calculate characters, right? We need to show that they are non-zero. And in our particular case, this self-conjugate partition is this one. And then the principal hooks are this arithmetic progression that starts from 2k minus 1 and decreases by 4. So let's take these numbers. So PA of M is the number of partitions of M, this number M, into distinct parts from this set. Number of ways to write M as sum of guys from, as this generating function defines it. So now what we can do using using Murnagao-Nakayama rule and Jacobi-Trulli identity, actually, if we have two rows, then this character, so if lambda has two rows, so it's this partition evaluated at this principal hooks, then we have this difference of this number of partitions into these guys here. And if it's a hook, then the corresponding character is again expressible through this, well, I won't say partition function meaning, but yeah, so these numbers. And now analysis comes into play where Ludwig's enrichment actually did asymptotics on this guy, these guys, and asymptotically proved that these are strictly increasing from some constant on. Well, now that they are strictly increasing, we can say that these guys are strictly greater than 0 from some point on, for all M greater than some constant, which so there is a more precise dependence. So these characters are actually strictly greater than 0, and similar approaches work when we add some more parts here, just that the expressions we get at the end are a little bit more complicated. But we can still use this analytic result to show that the character is non-zero. And then by the main lemma, these partitions, these irreducible representations are contained in the tensor square, and Saxel conjecture holds in for these cases. So now I want to talk about the next topic, which was not part of the original abstract and title. I want to talk about computational complexity, which is an unusual application of these notions and these ideas. So what is complexity about? So that's not about how complicated a formula is. It's actually about how quickly a computer can actually give you an answer. So there are two types of problems. So first of all, we always have some kind of input, and the input is in terms of bits. So if it's encoded by n bits, we say that the size of the input is n. And everything is in terms, so the complexity is now a function of n, of the size of the input. So there are two types of problems. One is decision problem, which is of the kind, is there an object such that so and so, so the answer should be yes or no. And then there are these complexity classes which are believed to be different. So P is the class of problems where the solution, so the answer yes or no, can be found out in polynomial of time, so polynomial in n time, so there exists some constant such that most n to this constant time can give you the answer. So then there is NP, which is a larger class of problems, which says that, okay, so maybe it takes exponentially long to come up with the answer, but once we know the answer, we can actually verify it, so we can exhibit some kind of witness that that proves that the answer is, let's say, yes. So if there is such an object, then we can describe this object and verify it in polynomial time of n. And so then there is, of course, the notion of completeness. So a problem is NP complete if every other NP problem can be reduced to it in polynomial time. So this is like an equivalence class. And there are some standard problems that are NP complete. For example, existence of a Hamiltonian path in a graph, which, so once I give you the Hamiltonian path, it's like it's linear time to verify that, but on the other hand, it's exponentially long to find it, to figure out whether one exists. And then there is an FPSAC problem, which is about solving systems, linear systems in integers. And then there is the other side, which is the counting problems, where we want to compute the value of some kind of function. So some kind of function in the input, and then there are these parallel notions to these ones here. So there is FP, where this is the class of functions which can be computed in polynomial time. They don't need to be polynomially large. So they can be, the answer can be 2 to the n, but once you know the answer is 2 to the n, you can write it out immediately. Or then there is the other class, so the equivalent of NP, which are the decision problems. There is the Sharpie analog, where this function is counting exponentially many objects, which are, however, verifiable in polynomial time. So, for example, if you want to count number of Hamiltonian paths, this is going to be a Sharpie problem. Or the quintessential problem in this, the ultimate problem in this class is actually computing the permanent of a matrix. Even if it's a 0-1 matrix, this is a Sharpie problem. This is a result by less variant from 30 years ago. And now, so of course there is the problem in this in this area. So is P equal to NP? Are these two classes equal, or alternatively, are these two classes equal? And then an approach was proposed maybe 15-20 years ago by Moumyuli and Sukhoni, which is called geometric complexity theory. And so, in brief, what they want to do is distinguish determinants which are actually computable in polynomial time thanks to their linear algebraic properties, and permanents, which I just told you are in Sharpie. And the distinction now happens in the language of algebraic geometry and representation theory. So this geometric refers to the fact that now the problems got transferred into algebraic geometry and representation theory. And let me show you what some of these problems are. So here are some of Moumyuli's conjectures, which need to need to hold in order for his theory to go through and show that P is not equal to NP. So there were some colors here, but I guess. So we have input are some integers n and l, then we have partitions which are written like that, so there's a sequence of integers. The parts themselves are in binary, but then the number of parts stays what it is. So then the size of the input is on the order of L times log n, so the parts, each of the parts in the partition is less than or equal to this number n, and there are L parts in each of these guys, so then the input size in binary is L log n. This is our n, this is what we want things to be polynomial in. And now there are these two problems. One is the decision problem, which figure out whether the Kronecker coefficient is 0 or not. So yes or no answer. The other problem is computed. So what is this equal to? So give the precise value. And here are Mullis conjectures. So he is conjecturing that the decision problem is in the class P, so it's polynomial, and that the enumerative problem or the computational problem, this is sharp P. Okay, so first of all, what is the motivation? The motivation is that the Littlewood-Richardson coefficients actually satisfy these conjectures. And the reason they satisfy them, well, for the sharp P part, it follows that from more or less from the Littlewood-Richardson rule, and they are sharp P complete, which is a result by Narayanan. Here, I think. And the fact that the decision problem is polynomial is actually a consequence of Knudsen-Tau's proof of the saturation theorem, and it's consequence of the fact that they are counting points in a polytope, in a particularly nice polytope, which has an integer point if and only if it is non-empty, and then it's just polynomial time to figure out if a polytope is empty or not. But notice that we don't even know whether this decision problem is in NP. Why is that? So we don't have any kind of positive formula for this Kronecker coefficient. We can't say that they are the number of such and such objects, such and such small objects. So remember, polynomially verifiable. So we don't want to do representation matrix, the matrices from the representations, because these are like huge. So we don't have any kind of combinatorial formula for these guys to tell us that even this holds, so not to mention about the polynomial. And the best thing we know so far is that they are so that's not Kp, but it should be Kn. So this enumerative question is in gap P, so it's a difference of two sharp P functions, but it doesn't mean that it's itself sharp P. And it can't be any better than that, so because of the Littlewood-Richardson coefficients, which are sharp P complete, and that being special case of Kronecker, then we know that the Kronecker, the computational problem is sharp P hard. So here is a result towards complexity. So what is this result saying is we actually give some kind of explicit bound on how fast we can compute these guys, these Kronecker coefficients. So suppose that one of the partitions has second parts bounded by some number m, which is also part of the input, and their length is L, then we can compute them in this time. So what does this formula mean? So first of all, these are our partitions. This is one of the partitions. Second row and below is bounded by this integer m. And suppose that m and L are small enough, but not necessarily constant, then this actually becomes polynomial in the size of the input. So if we have such restrictions, then we can actually compute the value of the Kronecker coefficient in polynomial time. For example, if one of the partitions is a hook, this is the case. And so moreover, if what happens if L is fixed, so this exponent is actually a constant. Now this becomes polynomial in the size of the input, and we recover a result of these people that computation is actually polynomial, takes polynomial to time. And there is another result which actually doesn't follow from this theorem. It follows from a semi-group property that there is actually a linear time algorithm to decide if L is fixed, so the lengths of the partitions are a fixed constant, then there is a linear time algorithm to decide whether the Kronecker coefficient is 0 or not. And this is actually an existence statement because the algorithm could be potentially. So we know that there exists an algorithm, but we can't write it down. Which is one of this. And the last thing is, I already told you there is one combinatorial interpretation, and thanks to that combinatorial interpretation, we can at least show that in this case, when one partition is a hook, then the decision problem is in NP, and the enumeration problem is sharp. And I just wanted to mention how these things work. So there is this kind of reduction lemma, which is saying that if one of the partitions has smaller second part, like is bounded by m, then we can actually say that the Kronecker coefficient is equal to the Kronecker coefficient of smaller partitions, which are, I mean, there is some kind of linear dependence from this lambda, mu, and nu. And we can also recover a stability criterion thanks to this result. So plus the fact that there is this semi-group property which says that if you have two sets of partitions with positive Kronecker coefficient, you can add them up and get this kind of inequalities. So it turns out that we have this generalized stability. If for any partition alpha, if we add a scaled version of alpha to two of the partitions and a very long row to the other partition, that this guy actually stabilizes. So it's bounded and is actually also increasing thanks to this fact. And so this is one of the results that Ernest mentioned earlier. And so here are more formulas. So one way to compute Kronecker coefficients is through some kind of alternating formula through counting contingency arrays, three-dimensional L by L by L contingency arrays. And the fact that contingency arrays are actually polytopes, we can compute the number of integer points thanks to Barvinok's algorithm in this type of time. So that shouldn't be max, but it should be log of this. Sorry. And then putting everything, so putting this together, we get an actual bound on the computation of Kronecker. And then with the reduction lemma, we get this characters, are they 0 or not, is actually NP hard, so that's characters are not gonna solve the other problem. And okay, so I'm out of time. I just wanted to say what this unimodality was about. Well, I will leave with this slide and stop here.
Any questions?
So, I mean, these Kronecker coefficients and Greta coefficients are counted by lattice points inside some rational polytopes. Does this say something about some conjectural polytopes that you can construct, maybe?
So the Kronecker coefficients are not counted by anything.
No, but if they were,
Yeah, so if they were counting number of lattice points in some polytopes which are sufficiently nicely defined through the data, that would say that the problem is in NP. But that would not be sufficient even to prove the first conjecture of Moll-Murray, for example. So you need not only a polytope, but a really nice polytope for this.
yeah, sure.
Yeah. So that would be a combinatorial interpretation that would be really nice if it was.
Any others?
Yeah, sir.
Yeah, so there's no idea on what restrictions there are on this polytope if there were such a thing.
No, there is nothing.
More? Okay, before I end this, let me tell you the next session will start in a few minutes under new management.